Hello, everyone. My name is Chris, and we're going to talk today about combined mode shaker testing. That encompasses sign on random, random on random, sign on random on random. And if that looks like alphabet soup to you, do not worry. We will get into the nuts and bolts and hopefully coming out on the other end with a better understanding of combined mode testing. This is just a glossary of terms. We're not going to be using all of these today, but it's good to know these abbreviations. I include them in presentations I do. Combined modes, what's going on here? So if you look at this video, you'll see there's kind of a base random excitation due to vortex shedding and all that stuff that happens aerodynamically. And then as the part fatigues, see this random behavior starts to turn more into a sine behavior. So there's this base random from all the engine vibration and everything going on. And then you have the sinusoidal component as the part gets into kind of a resonance condition. This is a great example of what we call combined modes, what you might also hear called mixed modes. It's a type of vibration test where you have a baseband, a base random excitation that's fairly low level with other non-stationary random or periodic components, or both. You see this in propeller aircraft, military jet aircraft, gunfire simulation, helicopters, tracked vehicles, automobiles. You ever hit the brakes really hard in your car and you get that nice foot massage? That is the anti-lock brake feature, pulsing those brake pads so the brakes don't lock up, and that gives you a kind of sinusoidal vibration on top of whatever kind of random vibration you're getting as you go down the road. Here's another two examples where you might encounter mixed mode or combined mode types, and also these are just cool videos, so I thought I'd share these. It's always fun to see helicopters fly apart, of course, as long as nobody gets hurt, right? So again, both of these are sinusoidal types of harmonics that are on top of a baseband random signal. That sound you hear when a helicopter passes by, that unique helicopter sound, is all due to blade pass frequencies and harmonics and all kinds of things going on. The start of the test is defining this broadband random signal that everything's going to ride on top of. And these are exactly the same as just a pure random test. And then you have signals that are going to go on top of this. As a kind of note aside, we're not going to talk about this today too much, but there's a multi-sign excitation where you can set up sweeping sine tones. So you break up a sine sweep into several components, or if you want to do just pure harmonic testing where you have a primary tone and then harmonics or blade pass frequencies or something like that, you can turn off the baseband random and do this multi-sign excitation alone. For most cases, when you're doing a mixed mode test, you define this broadband random background signal, and then you start to put tones on top of it. One option is fixed sine tones that have an amplitude and a frequency, and they can cycle on or off. You define an initial phase, but the sine tones don't move. The next layer of complexity here is sweeping sine tones, where you have a profile and a range and a sweep direction and an initial phase, and then you can define how this sweeps, and it can sweep back and forth and through this frequency interval that you define. And you can have multiple sweeping sine tones as well, up to 10 in the test lab software. This is indicative of like an engine that changes speed. So for instance, a propeller aircraft that's able to change how the propellers move, you'll see this type of phenomenon where you have all these sweeping sine tones superimposed that are the primary engine frequency and then the blade pass frequencies, and they can sweep up and down to simulate the engine changing RPMs. We'll take a look at that in the software too. The next type of combined mode is fixed narrowbands, which is the baseband random, but then you have these flat tones or bands of tones that go on top of that. And the profile here for fixed bands is always flat. You define a center frequency and a bandwidth. And this is more or less like a straight random test. You can define this in straight random and run it, but sine on random makes it much easier to do this. And also you have the capability of turning on and off these narrow bands, which is not a capability in just plain random vibration testing. And again, you can have up to 10 sweeping or fixed narrow bands. And what we're talking about with sweeping narrow bands is you define this profile and range and a bandwidth, and then the bands will sweep within the frequency range that is defined in the profile that's defined. And we'll also see that. Random on random is most typically used for tracked vehicle simulation. So you have tracked vehicles that have a base random excitation due to the engine of the vehicle and road noise. But then on top of that, you have these bands of random noise that are a factor of the tracks themselves and how long the links are and how fast the vehicle's going. And those bands will remain the same bandwidth, but they might change in frequency depending on how fast this tracked vehicle might be going. And then you can also combine all of these all at once, sweeping fixed sine tones, sweeping and fixed narrow bands can all be done in one test. You can overlap these, you can have them cross over. The software will handle that pretty well. There are some caveats that you should be aware of when doing combined mode tests. One of the big things is any of these narrow bands or tones that you describe, the amplitude should be at least 10 dB higher than the baseband random for good control. If you don't define that in the test, there'll be a warning that says, hey, it's a good practice to have your bands 10 dB higher than the baseband random, but it won't stop you from running the test, although it can be difficult to control that way. And the real reason for that is being able to separate out the bands from the base random signal and be able to control them independently. This is an idea of what's happening in combined modes for control. We have all of our signal acquisition, and then the software looks at the control and limit channels and makes sure they're within spec. If not, it'll abort the test. Then we extract the sine tones from the random and separate them, and there's a separate sine control loop and random control loop, and each one is controlled independently. It's worth noting, MIL standard 810 here, method 514 is a vibration. Within method 514, it talks about general vibration, but also part of it discusses mixed mode testing. You'll see tailoring guidelines in there, suggested test processes, specifications for material testing. For example, we're going to program into the software C130 test and a turbine engine test that is defined in the MIL standard. And there's also guidelines for developing test schedules, guidelines for analyzing results, best practices, and a whole bunch of references that you can look into. This is a great document in general, even if you're not doing DoD or required MIL standard type testing. There's some really good information in here, and it's available for free online. You can download it. Here's my copy of the MIL standard. I have little annotations in here as I go through. You can see it's over 1,000 pages, but dead useful document if you're doing vibration testing. You can also see some mixed mode or combined mode specifications in other standards. Feel free to look those up as well. But our main go-to in the US at least is typically this MIL standard 810, and we're at revision H right now. This is one test that we're going to run now. This is a C130 longitudinal transverse axis, and this is a very typical sine on random test definition. It gives you the baseband random and then these sine tones on top. And you can see the baseband random definition breakpoints in the PSD here, and the sine components in the middle, vertical axis in this section, and the longitudinal transverse in this section. The main reason I picked longitudinal transverse is you might see my little shaker there, and I don't feel like explaining to my wife why an armature has shot through the ceiling of my office here. So we'll be running this lower level test. The other test we're going to define is category 22 turbine engine vibration. And this is a narrowband random on random test, which is defined here. And these narrowband center frequencies are defined by the main engine rotation speed and then the harmonics of that. And the bandwidths are plus or minus 5% of the center frequency. So for this example, we're going to use an RPM of 15,000, which is kind of in the typical range. It's in the low typical range of a turbine engine, somewhere between 15,000 to 20,000 RPM is kind of a typical rotational speed of those engines. And we divide this by 60, and we get our first center frequency of 250. And we find out what the min and max are and determine what the bandwidth is going to be for those narrowbands. We're also going to use this as the basis of a sweeping narrowband test as well. Okay, so let's dive into the software here and see if we can't get in some trouble. So you'll notice the channel setup. You might have seen this before. The typical channel setup, we've defined the control channel as 0.1, and if you're looking in your video here, that's this accelerometer here in the Z direction. We're also measuring some other accelerations here, and I have a dynamic strain gauge or dynamic strain sensor and another little triax out on the tip here. So we can see how all this happens as we run the test. If you want more information on doing the channel setup specifically, we have articles in our community site as well as some videos online that deal with this specifically. And then we go into the random setup, and you might notice some of this looks pretty familiar. So this is our fixed sine tones baseband random from that C130 definition, MIL standard 810. Now, once you define that, what you're going to have to do in the random test mode, and again, this is plain Jane random control. The only thing we've done is gone to Tools, Add-ins, and made sure we checked these add-ins here for random on random and sine on random. And that will bring up these other tabs here in the profile definition where you can put your narrowband or sine tones in. So once you get that background PSD programmed, and we'll just take a look at that real quick. It's pretty straightforward. You get your frequency breakpoints and your amplitudes. And again, this is all pulled in from that C130 definition. And then we can go to fixed sine tones here. And if you click on edit fixed sine tones, you'll see you put in a frequency and an acceleration and startup phase. And you can put your alarm and abort limits in here. And then the other thing that you're going to see here is this time mode, on, off, and burst. So on means once you get to whatever level you define for these to turn on, the sine tone will start up after an offset and remain on for this duration. Off just turns this off and removes that tone entirely from the test. And then you also have burst, which allows you to set an on and an off time. So you can have these sine tones come on and cycle off. And that's typically used to simulate gunfire, where you can turn this set of sine tones on for a certain period and then turn them off for a certain period. I'm just going to leave this as on. And setting each sine tone is pretty straightforward. And again, these are based on the C130 definition, where you have a primary engine rotation speed and then the blade pass frequencies. It's a 4-bladed C130, so 17 times 4 is that first blade pass frequency, then double that frequency and triple that frequency, the blade pass frequencies for the harmonics. It's pretty straightforward for setting up just fixed sine tones. That's really all you have to do. One other thing to take a look at here is if you go into any of these advanced boxes, this is where you can set what level the sine tones turn on. So right now we're only turning the sine tones on after we get to 0 dB. Okay. We go into system identification. This was previously known as self-check. And again, system identification, system verification are new to TestLab 2206 release, replacing the self-check. But there's some pretty neat things that you get out of this system identification, system verification that are pretty unique to TestLab and dead useful. So we'll just hit start here. And you might watch your camera and see all right, so we have our self-test done, and we can go into system verification. The system verification is pretty neat because I can put up my responses and I can see what they're going to do. So for instance, I can see I'm going to have a big response with this PSD here, which is 0.6. And this might be something that I want to limit or reduce my levels. So this is based on a linear extrapolation from the pre-test transfer functions, but you can get a pretty good idea how the channels are going to respond and in what frequency ranges. So this will give you an idea before the test if you're going to hit any levels somewhere that are concerning for your test article and be able to nip that in the bud before it becomes an issue. Then we go into random control here and we'll hit ARM. And start. And now we can see our base random come up here. Now I have some time allowed for equalization, but this is looking good, so I'm just going to step up to the next frequency. I'll hit the next button here. Let it go for a couple control loops. Go up again. And again, if you're looking at your camera, or rather my camera, you can see what the test article is doing there. Go up to 0 dB now, and in a couple seconds those sine tones are going to come on because I programmed in a delay to allow this to equalize a little bit before the sine tones come on. That should start in about 10 more seconds here. Three, two, 1, and now we can see our sine tones coming up. And if you have ever sat inside any type of propeller type plane or even been close to one, it sounds very much like that with the sine tones on, where you have this base random noise and now the sine tones come on and you can hear what sounds like a propeller coming out of my shaker. All right, so let's go back to random setup here and see what a sweeping sine tone looks like. So we'll switch to this other section that I created, and you'll see my fixed sine tones went away. I'm still using the same background PSD, but now I have these sweeping tones that will go and run. In order to edit that, of course, we'll go and click this button, and you can see this is now looking more complicated. There's some sweep definition settings here, and these can be global or individual. Right now I've set this for global, so all of these are grayed out because it's all based on this total sweep time and number of sweeps. But you can set the sweep rates specifically if you go to individual here, and then if I want to edit that, I select this tone and I'll click on modify sine tone, and you can see how this works. In this case, I have this flat profile defined, but we can also change how that looks. If I want some type of sloped profile that it's going to sweep through, I can change that and give a slope to that band. And you can also see these upper and lower abort limits. This is just like setting up a sine profile. We set up a miniature sine profile, and then over here, we'll set our min and max frequencies for the band, the start frequency for the sweep at the startup phase, and you can set your individual sweep definition here, either by total sweep time, or I can change this to sweep rate and define it that way. And also the time modes here, very similar to the fixed sine tones, on, off, and burst works the same way. So you can have an initial offset and then an on time and an off time. In this case, I'm doing 0 offset, so these sine tones will start up immediately when we get to 0 dB. So I am just gonna hit cancel here and change this back to global, and this will define all these sweeps here. I'm gonna hit OK here, and let's go ahead and run this. Now, my system hasn't changed, so I'm not gonna run the system identification again. I'm gonna go to system verification and just double check that these predicted responses make sense. Still, they look very similar to the first self-check we ran, the first system identification. So I'm going to go right into random control. You can see I can arm this, and we'll be able to start. And again, if you want to watch your video as this happens, you can see how, again, this base broadband random has come up, and we'll hit next. Go to 3 dB, give that control loop or 2. Looks good, and I'm going to go to 0 dB now, and these sine tones will come on. So you can see it sounds on my end like a propeller plane when it climbs, and you hear the engine strain a little bit, and then it goes down in altitude and the engine runs a little faster. Go ahead and try this out on your own shakers. Hear what it sounds like, but it really sounds very interesting. So this is the idea. We're going to sweep back and forth, and currently I have these all synchronized as it makes sense with the rotating engine. These are all going to be linked to each other, what these frequencies are. So it's the same sweep rate going back and forth. It wouldn't make sense for this frequency to be going down and this frequency to be going up. You can also see down here what all the responses are in just the pure measured PSDs without the sine tones removed. That shows up as this lump in the measurement channel PSD. All right, I am going to call it quits there and go back to our random setup again, and let's take a look at fixed narrowbands. So I'm going to change to that section that I've already set up and see my sine tones have gone away. And now I have these fixed narrowbands based on this jet engine specification, or turbine engine specification in the MIL standard. And fixed narrowbands has you set a center frequency and then a bandwidth and a level. These can only be flat. You can't create a profile. If you want to create a profile, you have to do that in the sweeping narrowbands. And you can see there's the same time settings here: on, off, burst, offset, on and off, all works the same way here. And again, these will start up at 0 dB. So I'm going to hit OK here. And again, use the same system verification. And I can't stress enough that you have to be 110% sure that your setup has not changed. If you're not completely sure and comfortable, it doesn't hurt to run a system identification again and make sure everything is working out. It checks all the sensors. It gives you all this information about predicted levels and what the noise values are. And you can really see problems before they become problems by running a system identification. But again, I'm 100% sure that my setup hasn't changed. So we'll use this same transfer function data from before and start this test. And here we go, we'll hit start. So again, we start with a base random, and I'm gonna level up here. Looks good. Still looking good. Minus 3 dB. You might be able to hear this one a little better. It's a lot louder than the last test was. And I'll go up to 0 dB. But the narrow bands are about to come up, and there it goes. Okay, well, I can't listen to that much more on my end. Hopefully you caught a little bit of that as the narrow bands came on. But that's the basic idea for narrowband stationary random. And we'll also do some sweeping narrowbands here. I'll switch to my sweeping random on random definition. And my fixed bands went away. And now I've defined in advance some of these sweeping narrowbands. It's again based on the fixed narrowband definition. I just kind of made this up. It's very much the same as sweeping sine tones, where we're setting up individual bands here. And I can have an individual or global sweep definition, log or linear sweep mode, and different sweep strategies. And I put in what I want my total sweep time to be and the number of sweeps to do. This test is actually running for 2 minutes at the level, so I'll change this to 2 minutes so that the tones are sweeping throughout the whole thing. You can put in an offset here and some other things. Now, to create a band, I'd hit Add Band. Since I already have these, I'm just going to hit Modify Band and see what this setup looks like. Very similar to setting up the sweep for the sine tones. You set up your profile. The only difference here is that you're going to set a bandwidth for your narrow band. So this is going to stay at 25 hertz band, and it's going to sweep that 25 hertz band from 250 up to 300, and you give it a start frequency and start direction. And again, if I wanted to set these individually, I could change the sweep definition to individual. And now if I hit Modify Band, you'll see all this additional information pop up here. But again, we're just going to do pretty straightforward test, and this is based on a turbine engine, and that main frequency band is going to drive what these other frequency bands are. It's a multiplier of this main frequency. So again, these tones are designed to, or the way I've defined it, they're going to sweep in the same band. So the definition is the same for sweeping in each band. Now you'll see the bands get bigger as you get higher in frequency, and that is because these bands are defined in a percentage of that center frequency. So the bands are going to remain fixed, but increase with increasing frequency. Right, again, my setup hasn't changed, so I'm going to use the same self-test. And you can see here how this looks a little different in the responses that we're predicting. But let's go ahead and hit ARM and see how this goes. Again, we're starting down at 9 dB. I always tend to program a little more time than I need at these lower levels in case I do need some extra time for the control loop to equalize if I have highly nonlinear behavior, because I can always hit next and go up in level. It looks good, and our narrow bands, 0 dB. That's about all I can stand of that. Now, couple things to note here for this kind of test. Go back to this random setup and just look at some things. For these safety limits, by default, these alarm abort lines are set to 0, 0. This is how many lines you can have out of tolerance in the profile before the test will shut down. Now, typically, your spec is going to give you a number of lines out of tolerance that it's going to allow. Sometimes it's 0. A lot of times for these mixed mode tests, the test definition is a little more forgiving because it can be very difficult to run these. So there's a lot of things that you can do to tweak this to get it to run within the spec that you're given. There's some also other things that you can deal with to avoid having to increase these abort lines, like changing the degrees of freedom or some other options here that you can adjust with the control advanced settings. Also, you can run multiple control points. Sometimes that'll help with a very reactive structure to get kind of an average control. But that's about all I had. I'm going to put my last slide up here. This is my contact information. Feel free to email me, connect on LinkedIn.